Okay, so thank you very much. It's really a great honor for me to talk in front of the distinguished audience, but also this such a prestigious institution. And it's the second time in my life. So Walter von Donig, when he kindly invited me, he assigned me the title of this talk, What's Out There? So given the time, I'm sure that all of you know the answer. And the answer is that out there is lunch. And so I feel a certain responsibility to stand here between you and lunch. I promise I won't exceed my time. But going beyond the short-term expectation of a well-deserved lunch and taking a broader perspective about what's out there, I must confess that the situation is a lot less clear than the lunch ahead of us. Particle physics is in a very special moment. The discovery of the Broughton-Glare-Higgs boson, which was mentioned several times, has been really the coronation of a long journey of exploration of the particle physics world that led to what we call the Standard Model. So with that discovery, the field has reached a stage of maturity, and we have learned that theory, the Standard Model, offers a fabulously precise cartography of the particle physics world. However, we knew all along that there are questions that cannot be addressed by the Standard Model alone. So let me just give you just a list, but I could go on for 10 slides with question, how does gravity behave in the quantum regime? What creates the pattern of quarks and lepton masses that we observe? What keeps the electroweak scale light? What drives inflation? How do dark matter and dark energy fit into the picture? And we don't have the answers of these questions yet, and I could go on with a long list. If anything, actually recently we have made a step backwards in a sense, because many of the theories that we thought could provide some answers, or at least partial answers, to those questions are now disfavored by LHC results. So supersymmetry, technicolor, extra dimension, composite Higgs, which were traditionally what we were looking for, are by now either ruled out or really cornered. But I think there is right now in our field a sort of a silent revolution going on, in which theorists are trying to come up with really completely new ideas and new directions of research. The situation, of course, is still confused, but this is normal in a situation in which you are trying to really break into new territories of the mind. And this is also, in a sense, the best moment for theorists, especially young theorists that join in the field, because it's a moment of opportunity of asking new questions, when new ideas are really badly needed. So now I could give you an overview of the different attempts and approaches that are followed today, and that's how I started when I wanted to prepare this talk. But then soon I realized that probably will just end up in a long shopping list of disconnected ideas, because that's what's going on in the field. And many of these ideas we know that won't work will be eliminated soon. So especially to a diverse audience like you, I think would have been a rather boring shopping list. So I decided instead to follow a different approach and present you just one single topic. But I think that this topic will give you a good example of a story in which that represents what's happening in the field today. I will tell you a story that shows that how many different ideas and different expertise, theoretical expertise, is coming together in the description of a single phenomenon. And this is what we need for the future. Bringing ideas from various fields, bring them together to have address new questions. So the story I want to tell you is a story of black holes. And before I start the story, I should start with a prologue. So the prologue starts quite early, starts 1 billion years ago, when at the margin of the visible universe, two stars ran out of thermonuclear fuel and collapsed into black holes. Then, attracted by gravity, these two black holes started to orbit around each other, rotating faster and faster until they reached velocities close to the speed of light. And when the two black holes then come finally into contact and melt into a single black hole, they produce an incredible amount of energy. Within 1/10 of a second, they release an amount of energy equal to the energy emitted by all stars in the universe put together. Freddie tried to impress you with the energy of the LHC, okay? I'm doing better. But the question is, what is this form of energy? One could think maybe it's a tremendous roar. No, obviously that's impossible, because here we are in empty space. So it cannot be a sound wave, because sound doesn't propagate in empty space. Okay, so maybe it's some form of radiation or particle emission. No, again, it's impossible, because gravity is so intense around a black hole that all matter, and even light, is trapped and cannot escape. So what is this enormous energy emitted during the collision of the two black holes? What is it made of? And the answer is really something amazing, because the answer is that this energy comes from the deformation of space-time itself. We know from the general relativity that we interpret the phenomenon of gravity as a deformation of space-time. That's what's going on, because according to general relativity, the very structure of space-time gets distorted by matter. It gets warped, deformed, and, like in this case, can carry away a huge amount of energy, in this case, in the form of gravitational waves. Now, gravitational waves are not deformation of something that propagates in space, like the sound wave created in a car crash, which are propagating deformation of air density. No, gravitational waves are deformation of space-time itself. And this is the form of the spectacular energy emitted during the collision of two black holes. So this gives you simulations of the phenomenon, and you see, just in a two-dimensional space, it's represented the deformation of space-time as kind of waves, and as the black holes come together, the amplitude and the frequency gets faster. And then, when after the black hole relaxes into a single one, then there is silence. So during the billion years after that event, that collision between the two black holes, these emitted gravitational waves then silently propagate across the universe. And then, on September 14, 2015, which happened to be a Monday, they reached the Earth. See, at LHC, all those things happen during the weekend, right? But this has happened quietly on a Monday. So this is also is a simulation that shows that the effect of the passing gravitational waves, and as we get closer to the point of the collision, the effect is bigger. And there is a deformation of space-time with the Earth. Of course, by the time the gravitational waves have reached the Earth, after traveling a billion light years, its original energy, which is spread on the spherical wavefront, is almost completely diluted. Actually, at that point, is almost invisible. Contrary to what was shown in the video, in which you could see the Earth deforming, the wave deforms the entire Earth by a really tiny amount, something of the size of a proton. So we are looking at the deformation of the whole Earth of the size of a proton. Who could ever notice such a microscopic deformation? Well, this instrument can do it. And this instrument is LIGO. It's an interferometer made of 2 arms, 4 kilometers long, in which one shoots laser beams, which are reflected by mirrors located at the end of each arm. Here I'm showing you a simulation that shows that the 2 beams are split, reflected by the mirror, and then projected to a detector. Of course, light is made by waves, and so what happens is that when the 2 waves get together, if there was a distortion of space-time, so the distance traveled by light, you can start seeing a pattern of interference in your detector. And so you understand, and then you can be sensitive to distortions of the size of the wavelength of light. So by tuning the wavelengths, you can really go to really, really tiny deformations of space-time. So that's how gravitational waves were first discovered directly. Gravitational waves are a consequence of general relativity, as I told you. But how Einstein arrived at the result is really a curious story. So let me open a parenthesis, and I want to tell you the story. So soon after he proposed the theory of general relativity, Einstein immediately understood this similarity in the mathematics between his equations, the equation of general relativity, and Maxwell's equations, describing the propagation of electromagnetic waves. So it was natural to ask, do you have an analog for the Einstein equation? And indeed, he did what called Einstein equation, for the general relativity equations. So already in 1916, so immediately after, he had the claim that gravitational waves must exist. And actually, he concluded that they must be in 3 different kinds of gravitational waves. They had 3 different polarizations. Of course, we know today that's not the case. His conclusion was wrong, because he had just made a simple mathematical mistake in his calculation. And 2 years later, he corrected that mistake. But then, in 1936, now Einstein is a professor at Princeton, he got convinced of the opposite result. Gravitational waves do not exist. And he even wrote an article with a derivation of that, with all the calculation, and sent it to Physical Review, the major US journal in physics. The referee found a mistake in the article, and then in the report suggested a revision. When Einstein received the referee report, got furious. How could anyone tell Einstein that he's wrong? So he wrote a letter to the editor. He wrote it in German. He didn't even bother writing in English, saying, I had sent you the manuscript for publication and had not authorized you to show it to specialists before it is printed. I see no reason to address the, in any case, erroneous comments of your anonymous expert. And since that time, and you can check it, Einstein never published in Physical Review again for all his life. Actually, the referee was right. And Einstein was somehow too angry to even have the patience to read carefully and understand the argument. And it took him about a year of many discussions with colleagues, and finally he realized that his original conclusion was wrong. And he corrected, he gave a final publication, not sent to Physical Review, and where he stated that gravitational waves must exist. And this is the original article that now we quote. And he was right, of course. And that's how gravitational waves were discovered, theoretically. I think there is a moral to this story that we should accept as scientists, that errors are part of the process towards scientific discovery. This somehow, the public doesn't always understand. They think that science is a linear process in which you always go forward. I think that science does not advance linearly, but through some kind of random walk. But eventually, we get there. So even someone as great as Einstein can make mistakes. So this is a good lesson for all of us. We're not Einstein. So as Herman Melville said, he who has never failed somewhere, that man cannot be great. So I think this is a very useful quote to remember. Every time you make a mistake, think of that quote. It will put you in a good mood. So let's go back to the black hole and try to understand better what a black hole is. So a black hole is a region of space-time where gravity is so strong that it overcomes any other force. And so it does not allow any form of matter or radiation to escape. So black holes are objects that are so dense that if you want to make a black hole of the Earth, you should squeeze it into a volume of a glass marble. But the black holes observed by LIGO are not the size of glass marbles. They have a radius of about 100 kilometers. So they weigh roughly 30 times more than our sun. And gravity around a black hole is really insanely strong. Just to give you an example, if I would take an apple and let it fall on the surface of that black hole, after 10 centimeters, its velocity would reach 1,000,000 kilometers an hour. So poor Newton if they had the apple on his head. So seen from the outside, a non-rotating black hole is a perfect sphere, such that it is impossible to see its inside. So no signals that comes from the inside can reach any observer located in the outside of the black hole. So in this sense, a black hole is really a hole in space-time. It's a region of space-time inaccessible to any observation from the outside. And the existence of black holes as a consequence of general relativity was discovered by Karl Schwarzschild in 1915. So a few months after the publication of the original paper by Einstein on general relativity. And incidentally, Schwarzschild read the article by Einstein while he was at the military front as a volunteer in World War I. And then he died 1 year later, sadly. So the meaning of the Schwarzschild solution was very perplexing at that time. Einstein himself was convinced that black holes could not be realized in nature, and believed that the Schwarzschild singularities were only some strange mathematical pathologies that do not belong to nature. And in 1939, again, another mistake, he incorrectly argued in a paper that angular momentum of a collapsing matter always prevents the formation of physical black holes. So physical black holes cannot exist. Coincidence, the same year, 1939, Oppenheimer, and he hasn't even read the paper by Einstein, together with his student Hartland Snyder, computed the implosion of a star more massive than the maximum allowed for neutron stars, the famous limits that he had derived a few years before. And he argued that under these conditions, only gravity is important, and so you can simplify the calculation by neglecting any other force. So that calculation showed that from the point of view of an external observer, the collapse of such a star would come to a halt when the size of the star reaches the Schwarzschild radius, this critical value. When he said, in his own words, Oppenheimer said, cutting itself off from the visible universe. Then came the name of the whole. So Oppenheimer and Snyder effectively discovered black hole formation, although in the paper is really ambiguous because they did not speculate anything about the interior of the star or the collapse from the point of view of an infalling observer, which then would reveal the singularity, which is a big issue there. So because of these various approximations that Oppenheimer and Snyder used, this result remained controversial for decades. And After World War II, neither Einstein nor Oppenheimer ever came back to the question of black holes again. But others did. And today we know that black holes are indeed a real object. Actually, our own galaxy, the Milky Way, hosts a black hole with a mass of 4 million solar masses. So let's first try to explore now, let's say, such a large black hole, and we want to understand its inner structure. So imagine 2 astronauts sent in a mission to explore the structure of a black hole. Usually when you have 2 observers in general relativity, you call it Alice and Bob. But just to be more abstract, let me call them Charles Michel and Chris Peters. So the 2 of them travel towards a black hole, and once they get to a stable orbit around the black hole, they have to decide one of the 2 has to jump into the black hole, send signals to the other, just going to go measure. To make things simpler, let me throw into the black hole the francophone. In this case. So Michel takes with him a laser beamer that sends in the direction of Peters, who's orbiting around the black holes, intermittent light signals at regular intervals. So now I represent them by these red lines on top of this slide. So the question is, what does Peters see as Michel falls into the black hole? Well, Peters in the orbit receives signals separated by longer and longer time intervals. And also the color of the light changes, its frequency becomes lower and lower. So it's represented by those lines there. And this is the phenomenon called gravitational redshift, if you are familiar with that. So according to Peters, Michel takes an infinite time to reach the surface of the black hole. So Michel remains frozen in time on the surface of the black hole. This is, if you wish, exactly the result found by Oppenheimer and Snyder, that the star freezes. Actually, Oppenheimer was calling the frozen star. So time is frozen on the surface of a black hole. So now let's consider the different point of view, the one of Michel falling. So how does he see? What is the beamer sending? According to him, there's nothing strange. So during this free fall, his laser beamer emits lights always at the same frequency and at equal intervals. And what does he feel when he reaches the surface of the black hole? Well, nothing. There's nothing special. He doesn't see any time freezing. He doesn't feel anything going on. In his free fall, Michel doesn't feel anything special in crossing the surface of the black hole. He doesn't even realize that there is any surface. But of course, although he doesn't know, he will never be able to get out of the black hole. I think this is what happens in Belgian politics somehow. Right? So to understand better what's going on with a black hole surface, let me make an analogy that maybe you'll understand. So let's think of a river that ends in a waterfall. So the speed of the water increases as we approach the waterfall, as indicated by the blue arrows that are longer and longer as you get to the end. So now let's imagine a fish living in the river. The fish has a maximum swimming speed. It's indicated by the red arrow there. As long as a fish is sufficiently far from the waterfall, obviously it can swim downstream or upstream. However, when the fish reaches the point in which the current is equal to its maximum swimming speed, then it is doomed. So no matter how fast it tries to escape, it will be sucked down into the waterfall. Zoom. So, so there is a point of no return. However, there's nothing special in the river at that point. It's not that the color of the water changes or that there is a signpost telling you don't trespass this point, right? The fish will not feel anything special when it crosses this point of no return, although, of course, its fate is sealed. And the same happens for a black hole. Although there is a point of no return, or better say a surface of no return, there is nothing at the surface, because if there were something, then it would fall down, because, as I said, there's nothing that balances gravity, and gravity is attractive. So the surface of no return is called by physicists the event horizon. So the black hole beneath the event horizon is simply empty. But then the question is, what happens to Michel after crossing the event horizon? Well, he will keep on falling down into empty space, head first. At a certain point, he will start feeling a strong discomfort. This is when he starts feeling the effect of tidal forces. So let's say that he's falling head first. Since its head is closer to the center of the black hole than its feet, there is a gravitational gradient which will stretch his body. And sadly, his body will be torn apart long before reaching the center of the black hole. So Michel will never know what lies at the center of the black hole. So the question, do we know what lies at the center of the black hole? Unfortunately not. Because to understand, well, let me just, let me just first take a different perspective on how to address this question of the core of the black hole. So as I said before, stellar black holes are the result of the collapse of a massive star. And then they will get fatter by swallowing all the garbage that falls into them, acting as a sort of vacuum cleaner in the environment. So one would think that a stellar black hole is a very complex astrophysical object, exactly the opposite of an elementary particle, which is what we study at CERN. But that's not true. General relativity reveals an unexpected simplicity. So this concept is expressed by a rigorous mathematical theorem which says that a black hole is completely described by its mass, rotational speed, and electric charge. That's it. So these three numbers, which if you wish, are mass, spin, and charge, tell you everything about a black hole. In physics jargon, this theorem is called no-hair theorem. So black holes cannot have hair. Or better, physicists like this poetic touch, but black holes cannot have deformation. You see, planets are approximately spherical shape, but there are mountains, there are valleys, stars may have bulges, deformation, not black holes. In spite of being macroscopic astrophysical objects, black holes are ridiculously simple. A black hole is perfect and unique once you define mass, spin, and charge. So in this sense, a black hole is really a particle, an elementary particle, and it is the most perfect elementary particle that we can even imagine. So the difference is that black holes are elementary particles in which this classical event horizon hides to an external observer what happens at the core, at the center, at the singularity. And when we approach the singularity at distances smaller than the Planck length, gravity is so strong that the fabric of space-time is torn apart. We are entering now the regime of quantum gravity, where our current knowledge breaks down. We don't have a theory that can describe it. This distance, which is called the Planck length, is really infinitesimal. It is 10 to the 20 times smaller than the radius of a proton. So a black hole is empty space up to a central dot of volume roughly equal to the cube of the Planck length. So can we think of an experiment that probes the inner structure of the black hole. The probes really its quantum properties, so let's try. So at CERN we use colliders to probe small distances, and as it was explained beautifully by Jorgen, the higher the energy of the particle beams, the smaller the distance we can probe. So we need to collide particles at energies which are super Planckian. So let's compute the size of the collider that we need. So we take Lorentz formula, we plug in the magnetic field of the LHC dipoles, 8 Tesla, we put the energy of a Planck mass, and we find that we need a collider of a diameter of 10 to the 19 meters. This is almost the distance from the Earth to the galactic center. And the other question is, how long would it take to accelerate proton beam to that energy? So let's try using LHC technology. So in the LHC, you have 8 radio frequency cavities which are used to increase the energy of the proton beam by 16 MeV per round. So to reach Planckian energy, it would take about 10 to the 20 rounds, which correspond to 10 to the 13 times the age of the universe. And this is a long time, even for particle physics standards that we are used to make long-term planning. So there are really serious technical difficulties to build such a collider, but I have no doubt that genius of accelerators like Freddy Brodry will solve these problems. But for a theorist like me, there is actually a more conceptual problem. Even if we could smash protons at such an enormous energy, we could not test distances smaller than the Planck length. And the reason is that gravity would create an event horizon exactly like the one that we are observing for the black holes. So a kind of a cloak around the collision point, make anything inside invisible to us that we live outside. In other words, to resolve a distance as small as a Planck length, I need so much energy that the system collapses into a black hole. Okay, so we understood that black holes are these fantastic, simple particles, although we have problems at doing an experiment with them. But then this gentleman arrived and spoiled everything. Stephen Hawking and other physicists like Bekenstein, Zeldovich, and others, especially during the 70s, revolutionized our understanding of black holes, showing that black holes are not black, but emit radiation. And the most amazing part of this story is that the reason for this is quantum mechanics. I could give you an explanation of this, but maybe in the interest of time, let me skip the explanation of how Hawking radiation is generated. Let me just say that Hawking radiation, this quantum phenomenon that happens so that the black hole is not black but radiates, satisfies very strange properties. So one is that the more a black hole emits, the hotter it becomes. This is really counterintuitive, right? I mean, if I leave a plate of soup on the table, it gets colder with time by emitting heat. Well, a black hole does the opposite. So by emitting heat, it gets hotter. In a sense, the specific heat is negative. And the temperature of the Hawking radiation emitted by a black hole is extremely low. A stellar black hole is extremely cold. Just to, for instance, if I take the 30 solar mass black hole, like the one observed and made in the first observation by LIGO, the temperature is some billionth of a degree. So it's practically impossible to measure such a low temperature. So why is Hawking result so important? For a particle physicist like me, the strangest aspect of this story is that temperature is a characteristic of a complex system, not of an elementary particle, as I was interpreting before. So we cannot talk about the temperature of a single electron. It doesn't make sense. So I would have guessed the same thing for a black hole. On the contrary, a black hole shows that it's a complex system containing a huge amount of information, which is stored in a huge amount of possible internal states. What these states are, we have no idea. We don't know what they are, but we can compute that number of how many there are, and this number is huge. Just to get a feeling, and the calculation is very simple. You can really do it with high school physics if you know some thermodynamics, but I won't. Just to get a feeling of the amazing amount of information, I'll translate that information into what units that we're more familiar with. And in a black hole, which is 1,000 billion times smaller than a proton, I find a petabyte of data. So with a microscopic black hole, I could build a memory billion and billion times more powerful than any existing supercomputer. We have here Frédéric Hemer, who's best word expert in storing information. See, Frédéric, it's very easy. Just take a microscopic black hole, all your problems are solved. However, I must say that when you're looking at, by the way, the information is perfect in a black hole because it's perfectly maintained and then emitted through Hawking radiation, so you can read off the message there. However, these numbers are very impressive when I talk about size, but they become a lot less impressive if I talk about mass instead of size. So for instance, if I take this black hole device, which stores 1 petabyte of data, which is absolutely microscopic, right, 10 to the minus 12, the size of a proton, it actually weighs a kilogram. After all, I can go in any store and buy a terabyte hard drive, which weighs less than a kilo. So by smashing a hard drive or anything into a black hole, what you gain is in size, not in mass. And indeed, there is a mathematical theorem stating that in any given volume, nothing can contain more information than a black hole. So the question is, where is this huge amount of information stored and what is it? And here we really encounter another big surprise of black hole physics, because usually in every thermodynamical system that we are familiar with, the maximum information that you can store grows with the volume of the system. This is, I think, is completely intuitive, right? The larger the space you have, the more stuff you can squeeze in. But this is not the case for the black holes. So in spite of being the most efficient reservoir of information in nature, the amount of information that you can store in a black hole is proportional to its external surface, not to its volume. Or more precisely, if one computes the amount of information contained in a black hole as a function of its mass, you find that the bits of information are always proportional to the number of tiles that cover the surface of the black hole, where each tile has an area equal to the square of the Planck length. Again, the Planck length, the special unit that we have encountered already and which is characteristic length of quantum gravity. So even here, even the information, there is quantum gravity coming in. This result is absolutely shocking. You understand, just to make an example, it's like having a thick book and telling you that this thick book is the one that contains the most information in the universe, but then you learn that you can write only on the cover and the sides, and all the pages must remain perfectly blank. That's how a black hole stores information. So we are facing a paradox here. First, I was, on one side, I was describing the black hole as empty space, where all the mass is concentrated at the center, as an elementary particle, in a volume equal, this core has a volume equal to the cube of the Planck length. Then when I looked at information, I realized that the information is described by tiles covering the event horizon. So the square, so with tiles, with area equal to the square of the Planck length. So how can we reconcile these two interpretations? The short answer is that we don't know the answer. However, there are some intriguing clues towards a possible answer that has emerged recently. So clearly, we are dealing with quantity the size of the Planck length. So replying to the question requires knowledge of quantum gravity. And as I already told you, we don't know the correct theory. It's like one of the holy grail in physics, what we are trying to, is one of the questions we're trying to address. Well, some of these new theoretical ideas, what's called in jargon ADS, CFT correspondence, are suggesting a curious hint. A black hole may act as a hologram. So a hologram, as you know, is something that produces a fictitious three-dimensional image projected out of a two-dimensional photographic film. All the information about the three-dimensional image is actually contained in a two-dimensional surface. So black holes could work the same way. So the interior of the black hole is only a mirage. It's a fictitious image projected out of a reality that exists only on the external wall. So the two descriptions that I was giving of the black holes may not be contradictory because one is only the holographic image of the other. Of course, these are wild speculations and have been proven only for some spaces with strange curved geometries, which are not the one that we live in. But this is really a curious hint about the structure even of our universe. We know that astronomical observations have revealed that the expansion of our universe is accelerating, and the universe is doubling its size every 10 billion years. So as a result, further objects recede faster from us, and then at a far distance, galaxies move away from us at a speed faster than light, and so they disappear from our view. More precisely, they disappear from our view by crossing an event horizon. So this is exactly how matter disappears when disappears from our view after it's being swallowed by a black hole. So in this sense, our universe is a black hole in reverse. So using this analogy and taking the holographic principle to an extreme, we could imagine that the entire universe we live in is only a virtual image. It's a mirage of a reality that exists only in a lower dimensional space at the edges of the observable universe. Obviously, black holes still hides many unresolved mysteries. But I wanted to present this story because I think it's a prototype of what is happening today in theoretical physics. We are confronted with many puzzles, many fundamental questions that require bold new concepts and new theoretical tools. We still don't know how to properly address these questions, but we know that we need new radical ideas. Ideas that bring together different fields of research. You know, take the story that I was telling you of the black holes. Many different characters took part in this story. You know, from general relativity, quantum mechanics, particle physics, astrophysics, statistical mechanics, information theory, cosmology, all together are needed to understand this complex phenomena. So, to conclude, it's difficult to say what's out there, but that's what makes the game of theoretical physics so fascinating and so exciting today. So, we're all looking forward to explore what's out there, meaning lunch. Thank you.